All right, guys, welcome to another episode of Cuda Education. Today, I want to basically do a whiteboard edition of a small piece of the synchronization step for a small piece of the synchronization step for compute cloth, right? So we've been at this project for a while now, and we want to, we've talked a lot of stuff and been all over the place with it, but I think the whiteboard really just helps us to put everything together. So I intend for this to be a relatively short video, but I do have a lot of stuff to cover. So put on your seatbelt and let's go. All right, so this is Cuda Education. Right, and we're dealing with we're dealing with compute cloth.cpp, right? And the things that we want to cover are basically fences, semaphores, what else? Fences, semaphores. We're gonna get a little bit into Swapchain and presentation layer, right? All right. I might need the real estate there, so I'll just do Swapchain and presentation. Okay, but what we really want to do is just discuss, a small portion of how the how compute cloth works, mainly in the arena of the render function, right? So the render function is in charge of actually doing the render function is in charge of actually doing, the rendering to the screen, right? So all of what we're talking about is dealing with rendering to the screen. Okay, so we'll start with a basic overlay of how things go. So on one side we have the CPU, right? And then we have, I guess I'll just put it right here. We have a harsh, a strong division between the CPU and what we call the GPU, right? Okay, so we have our CPU and we have our GPU, okay? Within the GPU, we have just the general GPU area, and then we also have, inside of the GPU, so this is all GPU right here. This is all GPU, right? Inside of the GPU, we have a soft division, right, called the Swapchain, and then another soft division that we call presentation. Okay? So we have the CPU, which is your Intel AMD, CPU. The CPU is going to submit stuff to the GPU, work that needs to be done. Okay? So work that needs to be done. And and that's pretty much it. Once the work is done, CPU submits to GPU. Once the work is done, the GPU returns saying, hey, I've done the work that you have requested. Do you have any other kinds of work that needs to be done? And the CPU will then submit another request, and such and so forth. But in order for this relationship between CPU and GPU, we need to have what we call fences. Okay, so so we have what we call VK wait fences, right? And that's basically make sure previous work done before proceeding, right? Then we have VK reset fences. So reset flag to unsignaled. So a new VKQ submit can use it. All right. And then we have the VKQ submit. And really, as part of the submission, we also have fences, okay? And what that is submit work to GPU and also include fences so that CPU knows when the GPU has finished work. Okay? So here we have our submission. Okay? So we submit work to the GPU. So here in the GPU now we have in C C sharp, C++, we have, you know, these parentheses that basically just control scope. So we have we have compute, command, buffers, and we have maybe I'll do this in a different color. What do you guys say? We have graphics, command, buffers, right? And one second, guys, 1 second. All right, so basically what's gonna happen now is that we're gonna have to manage the relationship between the compute stuff and the graphics stuff, right? So we have Okay, so on the compute side, we have uh, we have a wait semaphore, and it's something like compute dot semaphores dot ready, and we have a signal semaphore called compute dot semaphore dot complete. Okay, and conversely on the the graphics side, we're going to basically have the wait semaphore is compute dot semaphore dot complete, right? And then on the signal side, we're gonna have compute dot semaphore dot ready. Okay, so notice, we're gonna notice now, notice that signal and the wait are the same, right? So these two guys are compute signals that it's complete, and graphics waits for compute to be finished. So notice that this is like a pair. So graphics is not going to start until it gets a signal from the compute buffers that compute has been completed. And then we also have this guy and this guy. Okay, so similar logic. Compute is going to wait for graphics to be finished. So compute isn't going to start until graphics is finished, right? So once graphics is finished, it signals that I've now finally completed my work. Compute.semaphore.ready is signaled, and then because compute has signaled that it has been complete, because graphics has signaled that its work has been complete, compute can now proceed with its tasks. Okay, so remember the application is a canvas falling on a sphere. Okay, the application is a canvas falling on a sphere. As the canvas hits the sphere, it contorts and whatever as a cloth would, as a canvas would, right? So you have to compute stuff, and then you have to display stuff as in, you know, graphics related things. So let's go through the loop again. Compute starts. Let's say compute says, okay, let's wait for the compute.semaphores.ready. You know, for maybe the initial condition, we just raise the flag as ready. So you know, compute command buffer start. It waits. It says, okay, it's ready. I'm gonna proceed with my work. Compute proceeds with its work. Once it's finished with its work, then once compute is finished with its work, it signals to the world that, hey, I'm finished with my work. Compute.semaphores.complete is now signaled as a flag, right? Onto the graphics side, the graphics is waiting for that compute.semaphore.complete to be signaled to say, hey, you know, we've been waiting on compute. Compute now says it's finally done. We can now proceed with our work. When we proceed with our work, we eventually signal that okay, compute.semaphore.ready means that, you know, we have finished our graphics work. You know, the world can proceed with whatever it wants to do. And as you can see, as you go through the line of logic, this signal, compute is waiting for graphics' signal, and graphics is waiting for compute signal, right? So that's synchronization in a nutshell on the GPU side. So notice that, as I always say, Semaphores is GPU related, Fences is CPU to GPU related, right? Semaphores are GPU to GPU processes. Now, as of the last time I checked, and I don't know if things have changed because they're always updating Vulkan, they're always trying to make improvements. But when I was learning this stuff, basically, Semaphores, you can't really query the status of the flags or whatever. All you could do is submit processes and declare how the relationship between the processes using the semaphores, right? So it's not like you could really query the semaphores. Now with Fences, you could sort of query it. You could say, okay, you know, what is the status of this flag? What is the status of that flag? With GPU stuff, with the semaphore stuff, as of what I learned when I learned it, you don't really have much control. All you could do is set up the work, set up the relationship between the work, and just know that when you make this submission, that the work is done as per your instructions, right? So that's sort of that's sort of this part of the equation. Now remember, we're dealing with the render function. So all of this stuff is basically, we're trying to build up to rendering something on the screen. Okay, so you know, so once all of this stuff is done, right, and you know, we may be looping through stuff and all of that, but I don't want to get too mechanical with it. But once the command buffer stuff has been executed, then the you know, then the processor basically it returns back to the CPU, right? And remember that, you know, we had our fences submitted, right? So the fence isn't gonna the fence isn't gonna change its color until all of this stuff is done. So okay, so here we're gonna have to put now we're gonna put signal fence that work is complete. right? So we signal fence that work is complete, processing returns back to the CPU, and then we redo the loop again. Now notice that VK wait fences, make sure previous work done before proceeding. So this guy is waiting for this right here. Okay, so once we signal work is complete, we're good. We can move along. But now we have to reset the fence. This is a very important step. Reset flag to unsignal so a new VKQ submit can use it, right? So once we return the processor back to the CPU and we said, hey, the GPU has done what you have asked, you have to reset back the fence because VKQ submit is going to submit another set of work to the GPU with, you know, with the fence being in a non-signal state and stuff. And we've tested this. If I take out the VK reset fences, the validator comes back with errors saying, hey, you know, it has, you know, VKQ submit was submitted with a signal fence, which is not protocol and all that stuff. So basically when we return back to the processor, we go back to VK wait fences. We go back to VK reset fences. And all of that stuff. So we basically, I don't know if you can see it here, but basically we repeat. You know, we start back over. So once we do this, we start back over here, right? We basically, we do all the stuff and we start back there, right? So that's that process, right? It's nothing too major. There is a subsequent step that the graphics portion has to do, right? So let me see if I could move this down a little bit because I need some space. There's also another piece that the graphics has to do, right? So the graphics has to, actually it's not even the graphics, okay? But so that's this process right here. But there's another thing that's going on the GPU. So once we do all the work, so we have the compute and we have the graphic stuff, and now we're ready to present to the screen. We have this thing called, and it's really part of the, it's really part of the graphics conversation, but actually let me look at it exactly how. Right, it's really part of the graphics conversation. So signal fences, da 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 da. And okay, so we have Vulkan example base dot submit frame, and then we have true. Okay, so what we're doing now is we've done all the work. We've done the compute stuff. We know, you know, what we're going to display and you know how we're going to display it, the colors, the vertices, all that good stuff. Now we have to present to the screen, right? And presenting to the screen, I'm running out of colors, guys. I'm running out of colors, but I don't even know if this is gonna work. All right, so presenting to the screen now, we basically have to deal with the swap chain, okay? So we're presenting to the screen. So what happens here is that we are building frames, right? So all of these is a frames, right? So the render function is a directly affects your frames per second. So I put a delay in the render function, and when I put a big delay, the frames per second drop to 2, 3, 4 frames per second. You guys know, you video game heads, that generally 30 frames per second is the minimal, 60 frames per second is ideal, and then of course there's more frames per second you could do to get smoother animation and all that stuff, right? So this whole process is just dealing with one frame, okay? But we're doing many frames per second, right? Ideally 60 or more frames per second. So we have to submit these frames. This work right here is building a frame. It's like you have a portrait. It's like you have a portrait, oil on canvas, right? A painting, and you're painting on that frame. That one frame, remember, 60 frames per second. That one frame. But now you have to submit that frame to the Swapchain, right? And the Swapchain is pretty much all the Swapchain is it's just a series of frames, okay? That's all. It's like a series of frames, okay? And there's a whole process that deals with that. It's a series of frames, and then, you know, we submit it to the queue of the Swapchain, and then we eventually make it to presentation, right? So presentation is your big monitor, right? It's your big monitor. So, you know, whatever it is that we have. So we have a sphere, and then we have, you know, the canvas falling down on the sphere, right? We have the canvas falling down on the sphere. This is computer monitor, right? Okay, but in order to manage this process right here, we have we have another set of semaphores. So the semaphores that we have here is you guys bet we have a wait semaphore and a signal semaphore. So I need to so we're gonna signal fences that work is complete, and that's that guy. All right, so as we have we signal the work back, but we have to submit frames to the swap chain that eventually make it to presentation, right? But we have to manage another GPU, the GPU process, in order for this to happen. And we have a wait semaphore equals present complete semaphore. Actually, right. We have a present complete semaphore, a wait semaphore, present complete semaphore, and a signal semaphore of we have a signal semaphore of render complete semaphore. Now, can you guys guess what the purpose of this set of semaphores are for? Present complete means that presentation has been completed on the frame. Render complete means that we have drawn the frame and it is now available for presentation. I don't want to get too much into this particularly at the moment, but just understand that we are dealing with we have to manage the process of rendering what we want drawing what we want and rendering it onto the frame and presenting it to the screen, right? So this process waits for the presentation to be complete before we start to do stuff on the frame. Once we do stuff on the frame, then we signal that, hey, render has been complete and that frame is now free to be presented to the screen. Okay, and that's pretty much what I wanted to discuss. This portion actually. There are different stages that are associated with the semaphores and stuff, but I don't want to make this more complex than it needs to be, right? But let us just go through one more time the entire process. So in the beginning, the CPU is VK wait fences. Make sure the previous work is done before proceeding, right? So VK wait fences is just making sure that any previous work that was submitted to the GPU is done, and we are clear to proceed. If work hasn't been done yet, we wait right here. Once we wait on the fence. We're waiting on the fence. We immediately go to resetting the fence. So when we wait on the fence, we wait on it to be signaled to say, hey, the GPU work is done. So once it's signaled, we immediately put the fence back in unsignaled state, right? Because we want to submit a new set of work to the GPU. So we wait for the fence to be signaled. We now have clearance to proceed once it's signaled. We immediately put the fence back in an unsignal state, and then we associate that fence with the VKQ submit that which is a new batch of work that we're submitting to the GPU. We submit VKQ submit with the unsignaled fence, right? We have to make sure that we submit the fence in an unsignal state so that the GPU can signal back to us that when the work is complete, it will signal this unsignaled fence to signaled, okay? It will change the unsignaled fence to unsignaled to signaled, okay? So we're submitting new work to the GPU, right, with an unsignaled fence. So we get to the GPU now. We have compute command buffers and graphics. Compute is mathematical calculations, right? So the cloth falling on the sphere is how the cloth, the canvas, how it contorts around the sphere. That's all math, you know, which is why math is very important, right? So we have math stuff that we have to do, and then graphic stuff that we have to do. Actually, for the graphic stuff, so the math stuff, the compute stuff is just the math. But then for the graphic stuff, we have to not only you know what we're drawing based on the computational results, but we also have to manage presenting stuff to our screen. This is our computer monitor here, right? We're presenting stuff to the screen, right? So the graphics has to manage its relationship with compute, and it has to manage its relationship with presenting stuff to the screen. Here, what we're doing in all of this, we're managing frames. A frame is just one picture, one square or a rectangle or however you want to call it, frame, and we're drawing stuff on the frame. But before we draw stuff, we have to know what we're drawing. That's what the compute stuff is for. And then we have to actually draw the stuff, which is what the graphic stuff is for, right? All of this is involved. It's a render function. This is all part of the render function. We're rendering stuff to the screen, right? If we slow down the render function, our frames per second drop. If we speed up the render function, our frames per second increase. 30 frames per second is the bare minimum, 60 is ideal, and of course greater is more silky smooth and all that stuff, right? So we have compute stuff, we have graphic stuff. We have to manage that relationship. Compute is waiting on semaphore.ready, compute.semaphore.ready. So it's waiting on this, and usually what happens is that what it's waiting on is for the signal from the graphics to be done. So it's waiting to make sure graphics could be done and blah, 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 right? So it waits on the dot ready. It signals the dot complete. Notice that dot complete here, the signal of compute is the wait for graphics. So this and this are tied together, right? So compute starts, once compute has clearance that it can proceed, it does its work, and then it signals that it's complete. That signaling that it's complete is what the graphics command buffer stuff is waiting on. So it's waiting for this to be complete. Once this is signaled as, once this semaphore is signaled as complete, remember we're dealing with semaphores now, not fences. Once the semaphore, once it's signaled as complete, now graphics can proceed with its work, right? Once graphic proceeds with its work, it signals dot ready, semaphore dot ready. So, and notice that this signal here is the wait for the signal for the graphics is the wait for the compute, right? So you understand the relationship between the two. But graphic side has to do more work. It also, after we build the frame and draw on the frame and everything, we actually have to present it to the screen. We have another set of semaphores that does that, right? That's these guys right here. And I'll just for a little bit of separation, I will just put this, you know, this is in relation to this stuff and this stuff, right? So we have to now present these frames to the screen. There's an intermediary step. This is all on the GPU now. This is all on the GPU. There's an intermediary step where there is the swap chain, which eventually leads to presentation to the screen. So it queues up all the frames, and then you present it to the screen. This actually is a lot more complex, where I have another whiteboard video where I talk about extracting a frame from the swap chain so we could draw on it, putting it back into the swap chain, and then it makes its way to the presentation. But we're not going to get into that complexity right here, right? So we have the wait semaphore, present complete semaphore, and the signal semaphore, render complete semaphore. So the graphics portion is waiting to make sure whatever frame we're working on, before we start working on it, we make sure that it is not being actively presented to the screen. You're not gonna draw on a frame that's actively being presented to the screen, right? And conversely, you're not gonna be trying to present a frame that you're actively drawing on, or you're actively, working on what you want to display. You're not going to be trying to present something that you're actively working on display. So that's what this portion of the wait and the signal semaphore is for. It's different from these guys. This is for the compute and the graphic stuff. This is for the frames that eventually makes its way to presenting to the computer monitor, right? And we have this Vulkan example base, submit frame, what have you. This Vulkan example base, it's a construct, a class, a reusable thing that's used across all of the examples that the author created. So he uses this standard submit frame function to basically submit frames for all of his examples. So that's why you have this Vulkan example base, because he's reusing components across all of the examples that we have, right? So we submit to the swap chain and to the presentation, right? Once we're done with all of that, signal fences that work is complete. So we actually signal to the CPU that that the work is complete. Maybe this could be, put down here. Is it really put? Where can I put that? Because yeah, I mean this is like right before here, so but basically we're signaling back to the CPU that, hey, as far as you're concerned, we're done with everything, and you could you could proceed. Just for completeness, maybe I will. Yeah, I mean I'll leave it, but basically this comes sort of before this guy, right? But we move back to the CPU that, hey, everything is done. Now we could go work on the next frame. So this happening for every, remember, 60 frames per second we're targeting or more, right? So this is happening really fast. And when I put a time delay on the render function, the frames per second drop naturally. But this is it, guys. This is Cuda Education. If you guys want to be able to have this stuff running on your computer, you need to get tutorial number 1, which installs the Vulkan API on your machine, and tutorial number 13, which installs all of these examples. I assume a Windows machine with a Vulkan-capable GPU. For this compute cloth example, you do not need ray tracing capabilities on your GPU. You just need to have it Vulkan capable. However, as part of the examples that you install in tutorial number 13, you're gonna have ray tracing examples. And the only way you could run those ray tracing examples is if you have ray tracing enabled on those GPUs. For NVIDIA, it is RTX capable GPUs and above, or later and greater. For Intel and AMD, I have no idea. Okay, but you need to make sure you have ray tracing capable GPU if you want to run the ray tracing examples. This example is not ray tracing, so you don't have to have it ray tracing capable. It just has to be Vulkan capable. But yeah, guys, this sort of goes through compute cloth. It's just a first step in understanding the whole chain of command. I highly recommend you guys check out the algorithm. I have a link to the algorithm in the description below. It's on GitHub, freely available. You could look through the render function and look through what I've displayed here, and maybe pick apart my presentation, or see for yourself what's going on in the render function. But computer graphics is cool stuff. Vulkan is cool stuff. For all of you guys artistically inclined, I highly recommend that you start on your journey of learning Vulkan. I assume no previous programming or computer knowledge with my tutorials. So even if you know nothing about computers, you could start on your journey with with the tutorials, right? I assume no previous knowledge. And this is about it, guys. We covered Semaphores, which is GPU, the GPU processing and relationships, and I covered Fences, which is CPU to GPU relationship, right? Managing that process. Now, tell me which ones you prefer, which ones you like. Do you prefer Fences or Semaphores? Which one you think is cooler? Tell me what kind of GPU you guys are running. Maybe you got the compute cloth installed on your machine. Maybe tinker with the code, maybe change it from a cloth to something else, whatever that's falling on the sphere, and what have you. Thank you guys for watching. Have a great day.